Series solution around ordinary point. Number one, we're going to define what an ordinary and singular point are. Determine the minimum value for the radius of convergence of a power series solution. That's something we need to take into consideration. And determine, of course, a series solution centered at ordinary point for homogeneous linear second order differential equations. I may do some non-homogeneous, but that can be later, not initially. Okay. Okay, well, let's consider the second order, second order differential equation with linear, by the way. I mean, again, by definition, this equation is linear if the variable, the dependent variable or their derivatives are only raised to the first power or they're not being multiplied by themselves, which is what we have, all right? We only have constant coefficients or potentially variable coefficients, but those variable coefficients are related to the independent variable, not to the dependent variable. Okay? You guys might remember we wrote this equation in standard form, if you will. That is an equation with a leading coefficient equals to 1. If our coefficients have variables, do you see how a sub 2 goes to the denominator? And if we have variables, those are potential zeros in the denominator. Those are the singularities, all right? We're going to talk about those singularities. Well, by definition, a point x equals x naught is said to be an ordinary point for the differential equation in one, the first equation, without the division by a sub 1, if both coefficients of p and q in the standard form are analytic at x naught. Oh, what the hell is that? Okay, a point that is not ordinary is said to be singular, the differential equation. But anyway, function? Well, a function is said to be analytic at x naught if it can't be represented by a power series centered at that point x naught with either a positive or an infinite radius of convergence. But still, what is that anyway? Well, alternatively, an easier way to see this, a number x equals to x naught is an ordinary point if the denominator a sub 2 of x is not equal to 0 in the differential equation. And x equals x naught is singular if it is equal to 0. In other words, let's have a look at one example. So consider the differential equation. Let's identify the singular points and just the singular points in this case. So let's start by writing the equation in the required form. Divide both sides by x squared minus 9. And that'll be the equation y double prime equals to, y double prime minus, not equal, 5 over x, the x that was already there, times x squared minus 9, y prime, plus e to the x over x squared minus 9, y equals 0. Clearly, there that is the values that make the denominator 0 in the differential equation. So I know that the definition is very technical, but translated in a way that we can easily understand. Well, whatever singular points are, whatever make the denominator equal to 0. We'll see an example about it. Okay, so I'm going to set x times x minus 9, x squared minus 9 equal to 0. That's x times x plus 3, x minus 9, factoring the difference of squares, and using the zero product property. We would get how many singular points? Zero, three, a total of 3, 0 in this case, -3, and +3. So these are singular. Unfortunately, in this course, we're not going to get the chance to solve differential equations around singular points. You're welcome. Ah, it's fun though, but yeah, one of those problems takes at least 5 pages to solve. So, yeah. Okay, guys. Now, again, back to properties of series. When we're dealing with an infinite series that will potentially be the solution to a differential equation, one thing that we care about is the rate, the interval of convergence, or just the radius. I mean, because again, the interval of convergence of a power series is related to the domain of the function that it's representing, right? So we don't want values for which the function is undefined. In this context, values where the power series is not convergent. So we want convergent, okay? So when we do all this, let's have a look at the next theorem. So given some series sigma n equals 0 to infinity c sub n x minus x naught to the n, that is the power solution to some differential equation so around the ordinary point x naught. So the minimum value for the radius of convergence for the series is actually the distance from x naught, that is the center of the series, to the nearest singular point. Wait, what is that? What is this trying to tell us? Have a look at the next point. This means that if a power series is centered at some ordinary point, x naught of a differential equation, the radius of conversion of convergence is guaranteed to be at least as large as that distance to the closest singular point. If we get past that distance, that means we're going to fall into the divergence region, or in the singular region, if you will, right? Number two, the series is guaranteed to converge for any point within the disk of convergence, which is the area within a circle of radius r around the center. Okay. Number three, the series will diverge for any point outside of the disk. Okay. Why not interval and why a disk? Because what if these singular points are complex numbers, right? So now we need to consider a disk and no longer just an interval. All right. So that's so if you gotta be freaked out about, wait, what disk? So we're talking about interval. No, no, no. So in this case, we need to consider the disk. Remember, like the limit definition for functions of two variables, we go we're bounded on a disk rather than just an interval. Well, so that's coming back. Okay, as an example, um, find the minimum value for the radius of convergence of the power series solution about x equals to 1 for the equation x squared y double prime plus y prime plus xy equals to 0. Start by dividing by the coefficient of y of the highest or derivative, in this case y double prime. This will be y double prime plus 1 over x squared y prime plus 1 over x y equals to 0. What are the singular points in here? Just one, in fact, right? So x equals to 0 is a singular point. All right. So find that distance that is the minimum value for the distance, I mean for the radius of convergence, is x equals 1 minus the closest singular value, which is 0, that is 1. So that means our series has to converge within a radius of 1, right? Close to the with 1 unit close to the closest singular point. Okay. Finally, solve differential equations using power series. Okay, so now we're ready. Yes.
So that 1 minus 0,
Mhm.
it comes from the center x equals 1 minus 0 singular
With a
point.
singular point, correct. Yes. Okay, to find power series solution to of the form to solve it D using power series. First of all, assume y of x equals sigma n equals 0 to infinity a sub n. Well, I actually had it as c sub n. It doesn't matter. A sub n, c sub n, x to the n. differentiate the power series to get y prime equals sigma n equals 1 to infinity and a sub n x to the n minus 1, and y double prime sigma n equals to infinity n times n minus 1, a sub n and x to the n minus 2. All we're doing here is simply general power rule, right? Number 3, substitute these expressions into the differential equation. Number 2, re-index sums as necessary to combine terms and simplify the expression. Number 3, equate coefficients of like power of x to determine values of the coefficient a sub n in the power series. Number 6, substitute the coefficients back into the power series and write the solution. And again, in some cases, we may be able to write the sigma notation in closed form. That's what we call it. In some cases, just a polynomial. And if we're able, again, to do this using sigma notation, um, we still may be able to find the function represented. Okay, here we go. All right, so sigma, okay, consider the equation y prime equals to y prime minus 2xy equals to 0. The question here is x equals to 0 an ordinary point or a singular point? Does x equals 0 make any denominators equal to 0 for this equation? Then it is a yes. It's ordinary point, all right? Okay. Otherwise, if x equals 0, made the denominator to 0, then it's a singular point. Okay. Find the general series solution to the equation around x equals 0. Okay, so start by y equals to sigma n equals 0 to infinity of a sub n. I'm going to use a, okay? So, yeah, a or c, doesn't matter. A sub n, x to the n, y prime, sigma n equals 0 to infinity n a sub n x to the n. Okay, guys, I know I already mentioned we were supposed to change the starting index for the derivative, but at least for this exercise, I'm going to keep it at 0. Again, it's like doing one of those incomplete shiftings. It doesn't matter if this starts at 0 or at 1. It doesn't affect anything, right? Okay, let's substitute into the differential equation. Substitute sigma n equals 0 to infinity n a sub n x to the n minus 1 minus 2x sigma n equals 0 to infinity of a sub n x to the n. And let that be equal to 0. Okay? Okay, guys, here is the tricky part of the problem. Combine the series into a single one. So I'm going to first introduce these 2x inside the sigma notation and leave the other one the same. Minus sigma n equals 0 to infinity of 2 a sub n x to the n plus 1. Agree? Okay. Okay, here is the tricky part. Number 1, we want the two series to start at the same starting index, which we have. Okay? We have a problem. The power of x is not the same, unfortunately. So, how many, okay, again, how many units are these two exponents apart from each other? 2 units, right? Okay, okay, the thing here is if I add 2 units, okay, I need to subtract the 2 units starting index. But that's we can't do that. We can't because for a power series we need starting index to go from 0 to all positives, right? So this is where so here is where make your wish come true, right? Make your wish come true. What do? Expand n equals 0 and n equals to 1, so that the remaining terms are a closed series with a starting index at n equal to 2. Okay, so 0 a sub 0 x to the 0 minus 1 plus 1 a sub 1 x to the 1 minus 1 plus sigma n equals 2, okay, to infinity n a sub n x to the n minus 1 minus sigma n equals 0 to infinity to a sub n x to the n plus 1, set that equal to 0, right? Okay, now, oh, like this, we could add 2 units, add 2 units, add 2 units, subtract 2 units, and we do two things in one shot. The starting index at n equals 0 for both, and the same power of x, all right? Okay, guys. This is going to go to 0. This is 1 times a sub 1. That's a sub 1. X to the 0 plus sigma n equals 0 to infinity of n plus 2 a sub n plus 2 x to the n plus 1 minus sigma n equals 0 to infinity 2 a sub n x to the n plus 1 equals to 0. So guys, at this point, can we combine the two series into a single one? We have the same starting index, the same power of x. A sub 1 x to the 0, isn't that just a sub 1? Plus sigma n equals 0 to infinity, that is n plus 2 times a sub n plus 2 minus 2 a sub n, and then x to the n plus 1 outside equal to 0. Okay, guys, just to relate it to relate this to something. I mean, how many of you are into video games? You know, Zelda games, for instance. So you go to a temple, you go to a dungeon. There's always a final boss, right? And there's always like a mini boss somewhere halfway through the temple or the dungeon. This part right here, the combining the series into a single one, this is the mini boss. All right, we're heading to the boss. We're heading to the final boss here. Okay, guys, for this particular case, what are we going to do? We're going to equate coefficients. What do you mean? Okay, isn't that 0 plus 0x plus 0x squared plus dot 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 plus 0x to the n plus 0x to the n plus 1 plus dot 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 and continues on and on. Does that make sense? You guys follow me here, okay? Okay. So, do you guys see this a sub 1? Isn't that just a number, a constant equals a constant, isn't it? From here, this means a sub 1 equals to 0. And this rule we have inside of the series, isn't that the coefficient of x to the n plus 1? But what is the coefficient of n plus 1 on the right-hand side? 0, isn't it? Okay, so that means we're going to set this guy equal to 0. Okay, what's next? So I'm going to, okay, n plus 2 times a sub n plus 2 minus 2 a sub n equals to 0. What is this? Okay, guys, expression I just said equal to 0 is what we call a recurrence relation. This is what we're going to use to generate the coefficients and eventually come up with a rule, potentially, if possible, or at least write the solution in polynomial form. All right. So here we need to solve this equation for the term or for a term that contains the largest subscript, that is a sub n plus 2. So n plus 2 times a sub n plus 2 equals to 2 a sub n. A sub n plus 2 equals to 2 a sub n over n plus 2. So this is the relation we're going to use to find the coefficients. Okay, guys, so we're going to start by substituting different values of n. Which value of n do we start at, guys? We start at the value of n, the same one as in the sigma series before solving this recurrence relation. So this is what we do. N equals to 0. That equals, okay, that's actually a sub n plus 2. Isn't that 0 plus 2, which is a sub 2? Okay, and that equals 2 times a sub 0 divided by 0 plus 2. Okay, uh, which is, in this case, 2 a sub 0 over 2, which means divide out, that means a sub 2 equals to a sub 0. So that's one of the coefficients. Guys, we're going to spend a good minute generating some coefficients here, okay? So let's continue. N equals to 1. That is, so that'll be, okay, let me actually highlight the recurrence relation so you can see where are we, what are we using to generate these coefficients. So that'll be a sub 1 plus 2. Is that a sub 3? That equals 2 times a sub 1 over 1 plus 2, which is 2/3 a sub 1. But wait a minute, guys. What is a sub 1 in this case? Let me actually highlight that. A sub 1 equals to 0, okay? So this is 2/3 times 0, so a sub 3 equals to 0. Let's keep going. N equal to 2. That is a sub 4, which is 2 times a sub 4 over 2 plus 2, which is 2 divided by 4. Okay, 2 divided by 4, c sub 2, which is 1/2 c sub 2. But actually, what is c sub 2? Wait, not c, a. I mean, because I have my notes with, yes, it's a, a. What is a sub 2? Isn't that a sub 0? So a sub 4 equals to 1/2 a sub 0. Okay. Let's keep going. Let's keep going. Soon we're not gonna have enough time. Anyway, we're gonna as far as we can. Okay. N equals to 2, 3 rather. Okay, this will be C sub 4. Okay, I mean a sub 5 rather. A sub 5 equals to 2 times a sub 3 over, what is that? 3 plus 2, which is 2 over 5. A sub 3. But again, what is a sub 3? Isn't that 0? So a sub 5 equals to 0. N equals to 4. That is a sub 4 plus 2. Isn't that a sub 6? Equals to 2 times a sub 4 divided by 4 plus 2, which is 2 over 6 a sub 4, which reduces to 1/3 a sub 4. But what is a sub 4? Isn't that 1/2 a sub 0? Are you guys following me at this point? Okay. So that means a sub 6 equals to, what is that? 1/3 times 1/2 times a sub 0. Okay. What's next? Let me do one more. N equals to 5. That's more than sufficient. So n equals to 5. That is a sub 7, which is, what is it? 2 times a sub 5 over 5 plus 2, which is 2 over 7, a over 5. But wait, what is a over 5? Wasn't that equal to 0? So a sub 7 equals to 0. This is good enough. Okay, now let's go back to what we assumed. No, 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 hold on. Let me do n equals to 6. N equals to 6. Okay, so this will be uh, c sub 8 equals to 2c, not c, it's a sub 6 over, what is that? 6 plus 2, which is 2 over 8, a sub 6, which is 1/4 a sub 6. But what is a sub 6? Isn't that a sub 6, so a sub 8 equals to 1/4 times whatever a sub 6 is, which in this case is a sub 6. Isn't that is a sub 6? Let me put it together. This is 1/3, 1/2, a sub 0. And this is good enough. Let's now write down the solution. Yeah. So our solution, uh, the solution of the form, which we initially called y equals to sigma n equals 0 to infinity of a sub n x to the n, which is a sub 0 plus a1 x to the first. Well, I'm not going to write the first x plus a sub 2 x squared plus a sub 3 x cubed plus a sub 4 x to the fourth, etc. All right. Okay, well, in this case, well, let me write a couple more terms. So this is an a plus a sub 5 x to the fifth a sub 6 x to the sixth plus etc. Okay. So, well, one thing you may have noticed is how, well, we use a different color to highlight this, okay? So how uh, all the odd number coefficients, a sub 3, a sub 5, a sub 7, in addition to a sub 1, remember, all of those have end up being 0. So in this case, how about, we simply cancel them out? Well, actually, I'm going to write them down, just to be consistent. Okay, so this will be y equals to c1, no, c0 plus 0x plus c0x squared. Actually, not c, a. What else? Plus 0x cubed plus 1/2 c0, I mean a0 x to the fourth plus 0 x to the fifth plus 1 over 3 times 2 a0 a sub 0 x to the sixth plus 0 x to the seventh plus 1 over 4 times 3 times 2, right? a0 x to the eighth plus infinitely many terms. And I mean, just to label what we had right here. So this is a0, which is simply a0. This is, what was that? Okay, so a sub 1, okay, this is a sub 1, this is a sub 2, okay, go back to a sub 2. What was a sub 2? Remember, a sub 0. A sub 3, remember, that was one of the 0 ones. A sub 4, okay, what was a sub 4? Go back to a sub 4, that's a half a sub 0, and then a sub 5, that is 0 again, a sub 6, that's 1 over 3 times 2, a sub 0, isn't that true? Which is this one right here, okay, and a sub 7, and then a sub 8. All right. Well, you might want to eliminate the zeros. Okay, let me just call, this is gonna go 0, 0, 0, 0. Okay. So, with after this cancellation, what we could do, notice how we have a common factor of a sub 0. So y equals to a sub 0 times, what do we get? 1 plus x squared plus x to the fourth over, okay, do you guys agree that this is 1/2, which is the 2 right here is can be written as a 2 factorial? The reason of this is because then we have 3 times 2, and then we have a 4 times 3 times 2. And if we continue the pattern, we most likely will get 5 times 4 times 3 times 2, which actually goes with the sequence of factorials. So plus x to the 6 over 3 factorial plus x to the 8 over 4 factorial, okay? Plus dot dot dot, all right? Now, in this case, what we could do is I'm going to rewrite the exponents because you notice how the exponents are twice the factorial that we see. And that's actually going to take us to to a nice looking series you will see. That is a sub 0 times 1 plus x squared plus. Actually, you know what? I'm going to rewrite this one as x squared quantity to the 0. And I'm going to write this over 0 factorial. So hopefully we agree that 0 factorial is 1. Any quantity raised to the 0 power equals to 1. So 1 divided by 1, it's still 1. Plus x squared, quantity to the first power, okay? That's divided by 1 factorial, which is the same term right here, plus x squared squared over 2 factorial plus x squared cubed over 3 factorial. And let me just write one more. X squared to the fourth power over 4 factorial plus infinitely many terms. And with this, we should be able to write uh, a nice series, a nice power series that is a sub naught. Okay, that's a sub naught times sigma n equals 0 to infinity of, what is that? In this case, that's x squared raised to the n divided by n factorial. So now we have a match between the factorials and the powers that we have. Now I'm going to read, this is actually the final answer as a power series representation. Now in this case, it's easy to write the actual function that is represented by the series, that is y equals to a sub 0 sigma n equals to 0 to infinity of u to the n over n factorial, where in this case u equals to x squared. And well, if we recall, sigma n equals 0 to infinity of u to the n over n factorial, that's actually the power series representation for the exponential function, that is a sub 0 e to the u, where u equals to x squared. All right, simply back substitute a sub 0 e to the x squared. Okay, and that is actually, well, if we wanted to write this instead of a sub 0, that's actually just a constant of integration, if you will see, e to the x squared, and that is the function. Okay, well, actually, for the power series representation, you might want to distribute the n. A sub 0 sigma n equals 0 to infinity of x to the 2n over n factorial. Much better, right? Now, let me go back to the original differential equation, So again, y prime minus 2x, y equals to 0. We can very well solve this differential equation using separation of variables. Well, so how about y prime equals to 2xy, which is dy dx, equals to 2xy. And well, separating the variables, dy over y equals 2x dx. Integrating both sides of the equation, we get ln of y, absolute value of y, if you will, equals to x squared plus c. And then exponentiating both sides on the base e, y equals, I'm going to make the absolute value bars at this point, okay? So that'll be e to the c e to the x squared, which is y equals to c e to the x squared, and which is the same function we got using power series representation.